Hey there. I think it's nearly lunchtime, and the drilling and the hammering and all that might actually come to an end. In the meantime, I can look at this picture. What I really like about this picture are those green eyes. Absolutely stunning. Beautiful eyes. Yes, the program. Or not the program. The program's not the goal, is it? The goal is to make splines. Now you see all these tests here. I've got them all lined up, just like before. And I renamed that toggle sprite to run debug tests. Something I can number define away in a release build were I were to make one. So it appears that the number of tests I currently have to run here is 8. Here's what the test does. Now, this is clean up this part. I declare an array of functions and call the test, one of the tests, the current test, and that returns to me how many functions have been filled in my array. And then I run through that many times, add the function, add a sprite to go along the function, and add the reason I have to add I wouldn't really have to add the sprites to the graph, except that they wouldn't get updated. That's the way they get updated. So I'd have to find another way to update them, or have them update themselves somehow, which could be possible. I could link them with their own animation timer. Oh, but the other thing is that when the graph needs to tell the sprites when the background's changed, so that's necessary. Draw the screen, invalidate the rect, and this here is just a macro that I have that cycles a counter. It does increments the counter, and when it hits this value, which is the number of tests I have, it'll go back to 0. Very handy macro. I have at and above. Actually, one of the macros that I don't know if it really crashed because of the macro, but I realized it was wrong, very much wrong. Where is that? What was that one? Oh yeah. Either only once or once every, or one of those things. I wonder where it is. Well, I don't hear much noise, so I think I can go ahead with this. Yeah, here. All of these things used a function call previously, a long time ago. We'll probably down here. I do a lot of checking in. I don't see it. My God. Look at all the times I've checked in since that. Here, whoop. I thought I saw it. Yeah, here. See. Diff assign, okay, is a thing that assigns to the left hand variable whatever's in the right hand and returns to you whether or not the value changed. I mean, returns true if that assignment did anything and false otherwise. Now, I ended up getting a crash on one of these, and I think it may have been because of a multi-threading issue. I mean, it's not thread safe to begin with, but calling a function and then doing an assignment in the function is a lot more dangerous anyway than what it is now. See, now once the thing has been assigned, in the case of this, only once is the important one, because that's one that it happens once and it'll never happen again. And in that case, all I want to do is just check that, like only access the variable and not be incrementing or calling functions when it's not going to change. So this logic turns out to be the same. Let's see. Dummy var equals false. Suppose dummy var is equal to false. It goes not, and if dummy var is false, not dummy var would be true. So therefore it has to check this condition, which causes an increment. And this is a post increment, so this will also be true. So we get true and true, and not true is false. It should come out true though. It's false, true, and not. I know it works. Oh, I think it evaluates from right to left, maybe. No, I'm sure it's left to right. Anyway, not important. We'll get back to that later. Hang on a sec, let me think about it. Okay, sorry. That's right. I didn't realize. It's the else. See, this does come out false the first time. This is true. Not dummy var, and not dummy var is also true, and it gets incremented at the same time as that is asked. And then not true is false. Exact once, not only once, exact once. Else, see? So it's on the else that you get in there. Next time through, it's going to try and do not, and then it's going to see that dummy var is already false. Not dummy var is false, and so it won't do any modifying of anything, try to assign anything. And at that point, that is thread safe, because multiple threads can certainly read from a variable that's not ever going to change. Okay, anyway, on to the tests. Now, what I want to do is I added a few little nifty features to this program, actually. One of the things that came up had to do with You know, I was saying that these little text things, it's slow to move them around because even though it's only invalidating its little square, it draws the whole screen. They're not sprites. Sprites don't. Sprite drawing is independent of what's happening with everything else. So I invented a thing that, well, I can use the mouse even now, and I can hold if I do Control click. I think is it? Oh, I have to be in edit mode. Yeah, see, I can move them around and move them somewhere else. But that thing that's moving around is a sprite. Like if I add a new text, I can still do this thing. At this point, it won't move the mouse because I use the keyboard, but that there is a sprite. So it doesn't matter how much stuff is going on with the screen. It's not part of the big picture, as it were. If I had a whole bunch of things, where it would be slow. Let's see, what else can I add? You know, here to move one of these things around would be extremely slow, but not if it's a sprite, because it remembers the background and does its own drawing. Anyway, that's just one of the things I did. Now, as to the tests, what I want to show you in this bit is one of the problems that I solved first, which is part of the problem of getting a decent interpolation between points. You know, we set down a bunch of points, and we want a nice graph, and we want our object to move smoothly at a constant rate of speed along that graph. By rate of speed, I mean pixels per second, basically. Okay. Now, this is a two-dimensional world, so there are no optical illusions should be apparent. You know, if it was 3 dimensions, sometimes it might be coming towards you or moving away and you can't tell. But in 2 dimensions, you can tell. Now, I don't know if my test will run with all the mucking around I just did, but okay. The first thing I did was I drew a parabola to see if it has any speed issues, and you can see that it does. There's some speeding up near the end. This thing's pretty solid now. I fixed this problem too. See? Just coming out of from one mode to another. I just had to check to see if it's in edit mode and enable the menu items, because the menu is recreated from scratch. Okay, so looking at this, you can see that it's not very pronounced though. So what I fiddled around. Well, I tried just doing to see if adding the full thing emphasizes it more, and it certainly, to me, it looks more like it's slowing down at the bottom of the curve, right? No, I don't. Let's see now. It's the formula. I can add text, can I? y equals x squared. How about yellow for chalk? Okay, so in terms of speed, oh my dot. Where is my dot? Oh, well, 2x. This is great. I can do this now. Right? Okay, so therefore at x equals 0, the speed is reduced to 0, right? And it increases linearly as you go along the curve. I mean, sorry, that's not true, is it? That's the slope of the curve, not the speed. But in terms, let's see, in terms of the parametric form, what we have is x of t is t, right? This will be more like chalk. And y of t is t squared, right? That's a darker one. So the position P is like that, right? Greater. Now, how do we compute the velocity of the particle? Well, we need to find out d by dt of this vector. Oh, I could use my arrows for vectors, maybe. Is it Alt 20? Not that one. Oh, now we're getting somewhere. Okay. So the speed that, well, the rate of change of P I'll do it this way. It's a function of t. I should have this thing remember the last color. I want my arrow. This is great. How do I draw a line? Underscore? It's great too because I can also delete them. Like that's too small. And dt, yeah, it should definitely remember the last color. Whoops. I'll get right on that. That is equal to the vector dx dt dy dt. That's the formula for the derivative of p with respect to time. Now dx dt is equal to 1. And then dy dt is 2t, right? So the speed at any time t is the root of the sum of the squares of these things. So v, the scalar v, or v squared, might as well use the square because I can't do a square root sign. That is equal to 1 plus 2 4t squared, right? Got the equals. Great! So that there is, so the square root of that, the minimum value is 1. It's not 0, right? In terms of the parametric form. It goes linearly, but it's the square root of this is a linear term, approximately 2t, right? It's approximately like 1 plus 2t. Right, which I could add. I could put that function in. We'll have to scale it by 100. It doesn't matter. 1, 2, everything else 0, minus 1, 2, 1. So this is going up to 150. Doesn't matter the scaling, does it? Well, yeah, that's right. But it could also be negative, right? And in this case, it starts out negative, and this can't be right. And it's positive, it switches from positive to negative. So the other solution is in fact from for t less than 0, it's the negative of this, right? Approximately. Minus 1 minus 2x. That would cross at minus 1. No, it can't be. The scalar velocity, its lowest point should be at t equals 1. T equals 0, sorry. And it certainly is. This graph, the square root of this graph is certainly not a straight line. So it's the square root of this. And it's not a parabola, but we could plot that parabola and try to imagine what the square root would look like. something like that. This meaning this is 1. Anyway, not important. I can delete that, and I can actually delete all these things without affecting anything. What I need is like a multi-select. I'm holding the control key down anyway. There. Okay, so now what I wanted to do is try to make this effect more pronounced. So I thought maybe a bigger parabola. And that appears to be, it's definitely more pronounced like this. Alright, now the next test, what I did was I split this into 2 and moved them side by side with no change, just to show them moving together. And now I'm going to show you the effect of the speed smoothing algorithm that I have. The one on the right is going to move at constant scalar velocity, and the one on the left will remain as it is. You'll notice that they reach the endpoint at the same time, but the one moving at constant velocity is ahead for a little bit because it's it catches it, whatever. This one's moving slowly for a while. Now you have to trust me that that's actually constant speed until I show you the code, and you'll see why. I don't think this is a glitch to do, not with the curve itself. It's just as smooth as this one, but the way I draw the curves is by giving equal weight to intervals of the t variable, you see. So therefore, the slow motion around a curve like this would be better drawn when the thing moves slowly, and there's more t, right? There are more t's. Whereas in the case of something that's moving quickly, it's far fewer t's. Okay, well I thought then I'd try a different curve to see if I can get something even more pronounced. And this is quite a, I think, very evident difference, right? This is definitely, if it weren't constant, it surely looks constant. So that's the time smoothing. And I did, now this is just as an example. This is our Hermite curve with some, I just fiddled with the parameters to try to get a good one that looks like it slows up and speeds up and slows down. And this one certainly does, I think. And I applied the speed smoothing to this curve, and that's the lower one. The lower one is smooth, and the upper one is not. And it definitely appears, at first glance anyway, to be solid, smooth motion. So those are my experiments. Okay, now how does it work? It's really quite simple. I have a new type of class, and that's being used here. in test 5. Is that the first place? I think so. That's the minus 2 to 2 parabola. You construct one by passing in a function and a number, which is a number of intervals that you want the function broken up into, because that's the way that this thing works. It works by breaking the function up into intervals of, let's see, are they equal length? They may not be equal length, but that doesn't matter. They're equal speed. Okay, so it'll be 200 intervals, each one having the property that the rate of change of position with respect to parameter is the same throughout. Okay, now first here's the declaration. There's not much to that. What is this now? I don't want H. This one. Okay, so it's now the smooth function impole, which takes a function and a number of intervals. Now this is the sanity check at the beginning. It has an array of things called line segments. So I've got so many different kinds of lines that this one I just added in wherever it is. It's not derived from anything. Where's the line segment? Is that it right here? Yeah, that's it. It just derives some refs, but it's not one of my function things. It looks like it looks almost exactly like the vector thing, which also has constant velocity, but its velocity is distance dependent. This one has this line segment. Well, I had an explanation here. Is one that has the property that the rate of change of distance along this line per unit time in pixels is the same as the rate of change of the parameter. So if the parameter changes at 10 units per second, then the object will move at 10 pixels per second. You see what I mean? And that's quite easy to demonstrate. It has a tangent, a direction like any line, an initial position, and a direction vector that's multiplied by some constant or some varying value, varying parameters, scalar. Now, when I did this previously, I didn't have minimum and maximum ranges. It was always 0 to something, and so in order to use that code with minimal chance of error, I just kept it as it was. So this thing is always going from 0 to something, okay, not 1 necessarily. And here's the thing. It's just standard parametric equation of a straight line, which is a known point position plus t-type scalar value multiplied by a tangent. But this is not a unit tangent. Or is it? It is. It's a unit vector tangent. That's correct. So since the length of this thing is 1, the length of the tangent vector, then the rate of change of this position with respect to time is simply ds dt times 1. 1 like ij1. How would I write that out in my fancy new lingo? So I have some vector in space. Oh, it's still doing that. I thought I turned that off. And then there's a tangent. Wait, not that. I don't want that color. And I want to turn that other thing off. Something more bland. Here is a vector in space. Now imagine that there's a vector, a tangent vector, a direction vector, let's say. Not, that is by definition tangent. Any direction vector, but the length of this is 1. Call this t for tangent. What color is it? And this has the property that t squared equals 1. That is, would be the dot product. If you know what dot product is, let me find my dot. I have a dot. I just don't remember the character code for it. Now, let me just, you may not know this. If you haven't studied linear algebra, there is a type of multiplication for vectors. Oops. And it's called a dot product. And that's what this here is. And the way the dot product works is if you have two vectors, v1 and v2, say, like that. Back to school, chalk. And another one, wait, before I do that. Another one, v2. It's moving up in importance, the yellow. Okay, then the definition of the dot product is a scalar quantity. I don't want to use that dot. I wish I had a smaller dot. Anyway, x1, how do I I'd like this to be a big dot and not a little dot, right? I need this to indicate that it's multiplied somehow. Y1, Y2, which is a scalar. So that's the definition of the dot product between two vectors. Which gives you a scalar quantity. Okay, and it's just the sum of just directly the products of the, if you look at this as rows and columns, the product of the numbers in the columns. If you had, three vector, right, there would be three element. Well, it's always two, so there's always only two things to multiply together, and then you add it up. So you can see that if you dot product something with itself, then that's just its x component squared plus its y component squared, and therefore that gives you the square of the length of the vector, and the square root of that is the length of the vector, but square root of 1 is 1. And so therefore I'm saying that this has a length 1. So our position, the position of a dot moving along this curve, I'm taking a long time explaining this, aren't I? Well, so it's some p naught plus s times regular times the t, right? I'll put this here, and I'll draw a line, try to make it go along there. Here is a position on the line, and its position, I don't know where that came from. Somehow I got a dot there. The position is given by this expression. Okay. No, well, I can't help it. Sorry. I want to be able to indicate where things are vectors. Okay. Now, just like regular calculus with one variable, if you take a derivative, things that are constant disappear, right? And if I'm differentiating with respect to the only thing that's changing here, s, I'm just going to get dp dt is equal to, this will leave me with t. This gives 0. The s disappears because it's 1. Its derivative with ds. ds is 1, so that just leaves me with t. All right. And that has a magnitude of 1. Right? Now, that's with respect to s. But usually, s is being the parameter is some function of some other variable like time. So let's suppose s is some function of time. Like that. New color. We're into the hypotheticals. Then what we have is dp ds equals dp ds, dp dt is dp ds times ds dt. You see? You see what that says? I should put this in brackets. This here, dp ds, is just equal to t. We already worked that out. ds, I'm going to try and make it look good at the end here. Now t here has a magnitude of 1. ds dt is the rate of change of s with respect to time. If for instance, if ds dt is 5 units per second, or 5 s's per second, then the speed in terms of pixels is 5 pixels per second. This is the length of 1. This ds dt is equal to 5, and this is written in pixel units. So the rate of speed is equal to the rate of change of position in terms of pixels with respect to time is always equal to the rate of change of the parameter. Okay, and it's the same, it's constant, and the same for all of those curves, all of these line segments. Right, now that took a hell of a long time. It did take a long time, but that was kind of fun. So now all this thing does, okay, is it has an array of these segment information things. This range at tail just is tells us at the end of this segment what it's sort of just keeping track, so we don't have to add things up. Keeping track of the range, the distance traveled so far by the whole function at the end of this segment. Okay. All right. So what does it do? Where's the implementation? Infos. Go through a number of intervals, taking position, the initial position at minimum, which I've in fact set to 0 to be consistent with before. So this is whatever I started out with. It may have had a negative t interval, but this doesn't. It only goes from 0 to something. In fact, this range at tail for the last segment would be the value of the line integral, the length, the actual arc length of the curve. Anyway, I calculate the position pos of the function passed in at the offset by the actual d min, which may be negative or positive, typically negative, and so since I'm out of sync by this amount, I have to add that back in to get the position for that corresponds with the position where I am, like when pos is equal to 0, this I should be computing func of min, right, and so on. Make a new line segment, compute its range by getting the range from the line segment, which has a range computation, right? Somewhere in here, here's its range. No, here's its range. It just evaluates itself at s equals 1. And that happens to be distance, the distance between the 2 points. So you can see its range is in fact the distance between the 2 points. And just add more and more of those line segments, this many of them, and now I have a collection of lines, and each of them have the same rate of speed. And to get the position pos at a given s, it's a matter of a binary search through the array to find which line segment corresponds with the given s. Okay, so how do I do that? First I start out in the middle. Let's curve max is the maximum value possible, and min is 0. Max is get upper bound. It's not size. It's valid. That's a valid index. Now I curve starts out in the middle. If the S is bigger than, remember S now is just in terms of length because we've given the range and the range is equal to the length of the curve. So if S is bigger than the range at the tail of the current segment, then we know that the minimum has to be at least one more than the current, and continue, and then divide again. Divide and conquer. If it's the other way around, it's a similar computation. There's no plus adding or subtracting in this case. In the case where S is less than the previous segment's range at the end, right? That means that the current one is the max. Let's see, if the current segment is like 6 or something, and S is less than the end of 6, right? Less than the end of 6, then the current maximum shouldn't it be this minus 1? It wouldn't really matter, I don't think. S is less than range at tail of the last of the one just before. What is max anyway? Max and min are going to be the same at the end. I think this actually could say I curve minus 1, right? Oh, yeah, it could. Because it could certainly be, it can't, I curves is not, I curve is certainly not in the picture anymore. This probably should say minus 1. I think. No, I thought long and hard a long time ago on this, so it's going to have to be a test. It should still work. I think that this assert might go off. Let's see, we'll see. I think it should work and actually be a little bit quicker. It'll be one fewer searches in the case where the actual min was I curve. If this might cause this to become these to become equal. Instead, see here, I'm just setting them equal. Because there doesn't seem to be another case. Let's see. Well, either it'll crash or seems to be working. I think that's right, it's fine. That might seem like that's a lot of computing to do for each point, binary search and find the line and so on. But actually it's quite fast. It's faster than doing cubes and squares and things, it turns out. I mean, computationally speaking, this is less demanding because you're only taking products of single products. There's no cubes or squares or anything like in here. Once you've figured out all of the line segments, it's linear. It's not even linear. It's logarithmic time to determine the line segment and the position along the line segment is just a simple multiply. Whereas for something like this, that involves a cube. And here, this has the 3 h's. It's got to compute with all those vectors. h1, 2, 3, and 4 is a lot more computationally expensive than this. Turns out. Or I'm proving it, but I'm pretty sure that that's the case. Okay, now so the next bit is going to be very trivial. We need to put these things together. What we have here is a thing that can take any curve and break it up into line segments that are equal speed. And what we do is we want to be able to do is make those tangent vectors as we go along with the dots. And there's an algorithm for that, and I'll explain that next time. All right. This has been far too long, but maybe it was fun. You want to look at the girl again? You have a look at her. She's quite pretty. How come I can't right click with my mouse anymore? Right click. I have to use the thing. I can't right click anymore. I have to use the right click thing on the keyboard. The one on my mouse just stopped working. Yeah, she's beautiful. Alright, next time.